So another example of direct proofs is the following. So I've been using theorem a whole lot, so let's go ahead and call this one a proposition. And typically, just like we abbreviate theorem as THM, proposition is often abbreviated just with prop right here. And this proposition is going to proceed as follows. Okay, so here's my proposition. If n is a perfect square, then n plus 2 is not a perfect square. Well, first off, you might not know the definition of what a perfect square is, so let's go ahead and define that right here. Okay, so n is called a perfect square if n is in, and then now I have this another notation right here. This right here is shorthand for the natural numbers right here. So basically 1, 2, 3, 4, etc. Like that. So it's called a perfect square if there exists another natural number such that we could write n as something else squared. So for example, nine is a perfect square because we can write 9 as 3 squared. And then 7 is not a perfect square because we can't write it as some other natural number squared. Okay, so that's what a perfect square is. So now that we know the definition, let's go back to our proposition. It again is stated in an if-then kind of statement. If it's a perfect square, then it's claiming that this thing is not a perfect square. Well, let's go ahead and start trying to prove this using our direct proof technique. Our direct proof technique tells us that we assume our hypothesis. Okay, so we assumed it's a perfect square. And just like in our last example, it's helpful to go back to the definition. So what does it mean to be a perfect square? There exists some other natural number that n equals k squared. Okay, so, well, I'm trying to get to my conclusion right here to show that n plus 2 is not a perfect square. So let's go ahead and do a little bit of scratch work on the side. So here we're going to have some scratch work. So I want to somehow connect up n being a perfect square to n plus 2 not being a perfect square. So, well, I could add 2 to both sides of this equation right here. So I could then write n plus 2 equals k squared plus 2 right here. And then to show our conclusion that it's not a perfect square would mean that I would then want to show that this k squared plus 2 right here does not equal something squared, where that something is a natural number. Well, that might be possible. You might be able to make an argument about using factoring or something like that, but that doesn't seem super promising. So, what else? What could we do? Well, first off, n and n plus 2, they're pretty close to each other, right? So while this seems a promising direction right here, it might be hard to proceed with that. So instead, let's think about n and n plus 2. They're really close to each other, which makes us think, well, if n is a perfect square, what's the next smallest perfect square? What's the next smallest perfect square? Well, the next smallest perfect square would be if I took this k right here and I just increased it by 1. Because remember, I'm only talking about natural numbers right here. And so the smallest amount that I could increase this would be by adding 1 to k. So we get that the next smallest perfect square larger than n is k plus 1 squared. I know it's going to be the next smallest one because that's the smallest amount that I can increase k right here. So let's go ahead and now use that and see if we can't somehow connect it up with n plus 2. So then, well, let's take this expression right here and let's go ahead and just expand it out. And then I get k squared plus 2k plus 1. Oh, hey, look at this. K squared, I know by my assumption in the definition right here, is just n. So I get n plus 2k plus 1. Why am I excited about that? Well, because I'm thinking about n plus 2 right here. So what's the smallest that this k right here could be? Well, it's a natural number, so it can only be 1, 2, 3, 4, 5, or stuff like that. So I know that this has to be greater than or equal to n plus 2 times 1 plus 1. And then simplifying that down, we get n plus 3. Ah, so the next smallest perfect square larger than n is going to be n plus 3. N plus 2 is smaller, and therefore it can't be a perfect square. And I can conclude. So once again, I have made my assumptions, and then I made an argument. And that gives me my conclusion. So I've been able to apply my standard direct proof technique. This actually is a very prototypical example of how a direct proof will actually proceed in practice. You're given something, you start out your proof, you use a definition, and then you sit. And you sit and you think, you do some scratch work, you try something out, you think, oh, maybe this will work, maybe it won't. You scratch your head a little bit and you think, and then you think a little bit harder, and then you come to a realization that, oh, maybe I should try this different route about the closeness of them. So what's the next smallest perfect square larger than the one that I'm considering, et cetera, and then that will lead you to an argument that will give you your conclusion right here. So these oftentimes take some thought to be able to construct this argument like this. So proofs, even though the direct proof technique is very powerful, requires some ingenuity and some creativity to be able to come up with an argument that connects up our assumption to our argument that allows us to get our conclusion right here.